Recorded is rolling. It is Monday, December 2nd. Yeah, welcome back from Thanksgiving break. You guys had a good break. So I got a lot on this page. Look at this. So there's a couple of files I posted to Google Classroom this morning. One is some updated posters. I'll show you guys where to find that and what those new posters are. Here, let's see. Also, here, I'm going to skip way down here. You guys see ELA testing for 9th and 10th grades tomorrow? I also posted that to Google Classroom. Let me show you guys exactly what that looks like. So here's, well, just for my AP class, but you guys, it's too much different, right? You guys see this one? This top one says Book of Posters, November 2024 edition, right? So over this semester, I've been making new posters. I cleaned them all up over Thanksgiving break and posted them. So yeah, if you guys download that one, there's a bunch of ones that are not in your thumbnails or that were not even in existence back in August, but they exist now. I'll show you guys some of those here in a few minutes. Also, do you guys see this one says Testing Tuesday for 9th and 10th grade? A bunch of my classes have some 10th graders. Some of you guys might be in 10th grade. If you're in 10th grade or if you have some friends who are, then definitely download this file right here, this Excel file, because there's testing tomorrow. It says where you're going to be testing. Okay, you guys got that? Okay. So two good files on Google Classroom that I just posted this morning. All right. All right. So right before the break, you guys did a lab. You guys remember with the collision carts? You guys remember these collision carts? Right. So it's the Friday right before the break. So one cart was just sitting here, another cart ran into it, and then it had some magnets stuck to them so they would stick together and just keep on rolling. Right. You guys took some measurements. You guys did some calculations, and this is what you guys were testing: was is this property called momentum conserved? So this is what we're getting into. Okay. So momentum, mass times velocity. Here, so I'm about to jump into that. Okay, so just giving an overview right here. What else got lined up this week? I've got some labs lined up. We're going to bring up the collision carts again and do the lab on the other side. You guys did hold on to that paper, right? You guys remember I put the turtle stamp on it? You guys keep that paper? Because on the opposite side is a little bit different setup, also with the collision carts. Also got some bouncy balls. So I got this bouncy ball. I got this not so bouncy ball. I got these tennis balls. We'll do a lab later this week. Says how bouncy is the ball. It's related to this content. Since I'm making a video for all my classes, my AP students have a progress check due 1 week from now in the morning, so we can go over that. It's on momentum. It's unit 4, multiple choice. Okay, I just show you guys this Excel file. This shows testing for 9th and 10th grades tomorrow, where you're going to be testing. Okay, so here's how we're going to finish out this semester. So I'll give you guys a quiz on this material that we're going to go over today and throughout this week, momentum. All right. So there's going to be an energy and momentum in class quiz. So no more take-home quizzes, at least this semester. So maybe next semester, but so no more. There's no more take-home quiz. I'll give you guys an in-class quiz on energy and momentum. It's going to be 10 questions each. So 10 on energy, 10 on momentum. I try to keep it like pretty fundamental. All right, so maybe there's a few equation type questions. There's some conceptual type questions. Things I think you guys will be able to do in class. Okay. Then by the end of next week, we'll have done the midterm review. So that'll probably take us about 3 days, I'm thinking, somewhere thereabouts. Okay. And then the midterm is going to be the week after that. And that'll take us all to Christmas break. All right, so you guys good with what we're doing next year? All right. All right, so let's go back to the top here because I do want to show you some of, at least some of the new posters that are on that file that I just posted this morning. Okay. Some of these are, well, here, you guys can see. So commonly used Greek. I actually did turn this into 2 different posters because it really needs to be on 2. It was kind of too crowded to be on 1. So you guys see like all these Greek characters here, and then on the other one, all these Greek characters here. Okay, so either you've seen these so far in this class or you will see them next semester. So one or the other. Right, so those are some commonly used Greek letters. Right, and what we're going to use them for in physics. Right? Ooh, algebra shuffling. Here's a really good one. You guys know how critically valuable algebra has been to solving equations in this class, right? You got to subtract this, divide by that, and so on, so you can isolate variables, right? So here's a really good exercise: is say I actually just have these 4 characters, A, B, C, and D, right? What can I do? Like, what combination, right? You guys see 1, 2, 3, 4, 5, 6, 7, 8 different boxes. Every single one of these boxes says the same thing. So, for example, let's make A equal to 8 and D equal to 3. Guys, what is 8 times 3? Is that 24? How about this? What if B is 6 and C is 4? What is 6 times 4? It can also be 24, right? Right. So 8 times 3 could be 6 times 4. Right? And if you kept those values for A, D, B, and C on this whole page, then every single one of these expressions is true. Like if I had how'd you guys solve for A? You could rearrange it and make it look like this. A equals BC divided by D, right? Or sorry, or what about this? What if you have a fraction divided by a fraction? Do you guys know you can take the bottom fraction, flip and multiply it, and it could be like that? You do that too, right? So if one of these is true, all the other expressions are true. This is really good to be able to do. Hopefully you can do this at this point, right? And if you're still really rusty on algebra, then definitely download that file. Take a good look at this one. Maybe pull out a blank piece of paper and see how far you can take this algebra shuffling. Yeah. All right. Oh, range formula. This goes way back to kinematic days. So if you launch a projectile, suppose you know the speed and the angle that you launch it. You can determine exactly where it's going to land, how far downrange. The answer is this green expression. What's new about this is I have all this derivation here. Like, where does it come from? Newton's first law. What's new is the word net. You guys see external net force on your thumbnail back from August. I just didn't have the word net, but it really needs to say net. Okay, so we got that. That's a little bit new. Some of these are just tweaked a little bit. This one's a new one. Incline outward. This one's a little bit involved. I more tend to ask AP students like this type of question, but that one's good one to have. Some of these are just like little tweaks. I updated this table a little bit. Centripetal versus centrifugal. I get that question all the time, so that was worth turning into a poster. This one I just tweaked a little bit, but it's basically not that different. Ooh, hey, this one's new. Earth and the moon to scale. Like, what's the size of the moon compared to the size of the Earth? And then if you said, what's their distance? So suppose you back way up in space and like looking through a telescope. Yeah, that's the distance from the Earth to the moon, like to scale. The Earth is the moon is 60 Earth radii away from the Earth. That's what it would look like. Okay. What's the density and gravity field of a planet? You know, the mass and the radial size of the planet. Universal gravity constant. That. Okay. Ooh. Suppose you're looking on Wikipedia. Like, hey, I wonder what is the mass of Jupiter, or what's the mass of Saturn? What's the mass of some planet? Like, and there's some number there, some number of kilograms. Like, how do they know? Like, how do they know what's the mass of any of these planets? Right? Well, you can figure out real fast if you just have if you just watch a moon orbiting the planet. Jupiter has lots of moons orbiting it. Saturn, same story. Right? So if you know how far away is that moon from the planet, that's this R right here. If you know how much time it takes to go around, that's this T right here. And you know universal gravity constant, you can solve for the mass of the planet. Okay? You can derive that from orbital speed. You can derive that from Kepler's third law. There you go. So that's a fun one to get. I think I may have asked you guys this question before. Hey, you guys have probably seen this question. Now you have a poster for it. All right, lever lab. Oh, modified outward with energy. Right. So follow some distance. How fast is it going? Speed. You do a conservation of energy setup. That's a pretty good one. Okay. Ooh, the spongy jumper. I stole this one from an AP question. There's a free response question they had back in the day. Right. But I think I asked you guys this one too, right? Okay, so bungee cord stretches by some amount. Here could be a conservation of energy setup you could solve for different things. Okay. Ooh, do you guys remember that in-class quiz you guys took a couple weeks back? One of the questions looks a lot like this. There's a car that just coasts uphill, right? And because it's going uphill, it's slowing down. Even if there's no frictional losses, that's still true. So maybe how fast going to the top or how high is the hill? Okay, here's the energy setup down here. Looks like this. Kinetic goes to potential plus kinetic. Okay. Ooh, efficiency. You guys remember this pulley? Here, look at this pulley system right here. You guys remember building some pulleys? And one of the questions I asked you is, what's the efficiency of the system? That's this Greek letter eta for efficiency. And one of the expressions you could use is, what's actual compared to ideal mechanical advantage? And you go, oh, it's 95% efficient. So you guys remember doing that? Okay. Here's different perspectives on efficiency. They'll all give you the same result. Here's a little graphic. So efficiency, I can get that. Okay. Oh, and then I have a bunch of purple banners. And we haven't even hit these purple banners yet. So we're going to have to save these for January. But it's really to rotational dynamics is what it's going to be. So yeah, I got a bunch of those new ones too that are not on your thumbnails, but if you want the new purple ones also, or any of those, that's all on that file. All right, so that's this right here, new posters. All right, so you guys ready for momentum? Momentum. All right, so I think you guys did see this one briefly, but like a week and a half ago. So let's do a quick recap here. There's this property in physics called momentum. I'm going to use the letter P, and all it is very simply is mass times velocity. Hey, what's those little arrows above the P and the V? What's the little arrow mean? It means what? It means it's a vector quantity. Yeah, it has a direction associated. That's right. That's right. Yeah, has a it's a vector value. Right? Now you guys know in this class there's scalars and there's vectors. If it's a scalar, it has some magnitude. You can plug it to the calculator. If it's a vector, it also has that, but it also has a direction. Yeah. So it could be forwards or backwards, right or left. Right? And that's going to be a critically important part of this section, this unit, momentum, right? This is a property that's conserved during collisions. Whenever you see a collision, right, then you're going to want to use this framework. I just gave you guys this half page as you walked in class today, right? And we're going to solve a bunch of these involved collisions, right? We won't solve the whole thing today. We'll get as far as we can, right? So mass times velocity, right? Right. Now, if you think back about 2 weeks ago, we were working with energy. Energy was a scalar. So, for example, kinetic energy was 1/2 mv squared, but it didn't really matter the direction if someone's going up, down, right, left, right? But now it is going to matter. So, if two objects are colliding, if they're heading, same direction, how versus opposite direction, how, that's going to be different types of collisions. Okay. Right, you guys good? All right. Now, this one, you guys also know a little bit about already, right? Perfectly inelastic. This is one type of collision. This is actually a one end of a spectrum of collisions we're going to look at. This is two objects collide and stick together. And you know about this one because this was the last lab that you guys did. Remember these collision cars? They had magnets stuck to them. One was just sitting there, the other rolled to it, and bam, and they rolled together. You guys remember that? Okay. Actually, you guys had a simplified version of this. So if I take some sticky notes and cover up some of this, if I cover up this right here, boink, and cover up this right here, boink. This was your lab. You had one cart just starting at rest, another cart was rolling into it, and they stuck together and roll off together. Okay. Right? And this is what it would look like. So all the momentum was provided by one cart. Then the carts stuck together. They made one giant mass. They moved together at a common final velocity. Wasn't that exactly what you guys just did in your lab? You guys had that lab paper? Right. Now, if I take these sticky notes off, then you get a little bit more complicated version of this, right? Which is, well, maybe this one was possibly also moving too. Right? I have a head-on collision. These are all just in one dimension. We're just going to focus on one-dimensional collisions, right, for the most part. Right? So then in the equation, you have to update the equation down here by saying plus and then MBVB not down here. Right? Now, if you do this, you guys see how these two are headed in opposite direction? Right? Let's think about what that would mean in terms of momentum. Let me give you guys a simplified version of this. What if the masses were the same mass? Do you guys see the same mass here? What if you have the same speed but the opposite direction? Okay? And they stick together. What would happen when they stick together? What's going to happen? Are they just going to come to a dead stop? If they have the same mass and same speed, opposite direction, they stick together? How many of you guys think they would come to a dead stop? Yeah, they sure would, wouldn't they? Suppose these are asteroids in space. How? Something like that. Okay? And after they do, at a dead stop, how much momentum is that equal to? 0. It wouldn't have any momentum at all. But hold on a minute, I thought momentum was conserved. Well, if you have 0 momentum after, then how much momentum was there in the system ever to start with? 0. Hang on, how can that be true? What if this is like 1 kilogram at 10 meters per second to the right? This is 1 kilogram at 10 meters per second to the left. Guys, guys, opposite directions, you need a negative sign. Guys, it's 1 times 10 plus 1 times negative 10. That's why it's 0, right? Okay, and that goes back to this being a vector quantity. Okay, that's why it's important, vectors, and you have to consider direction. Okay, is that too? All right, let's try one of these out. All right, you guys want to try one of these out? So we're gonna do a little bit strange order here. All the equations you need are in this box if you want to reference those. Also, all these posters are hanging in front of me here. Right, we're gonna start with number 5. You guys see number 5 down at the bottom? Two objects colliding stick together in a perfectly inelastic collision. Hey, that's this right here. Same as your lab back on Friday before the break. Right? That's what perfectly inelastic is. They stick together. Given the masses, all right, so there's mass A, mass B right there. Okay. Again, all of us have different papers, different numbers, but the same scenario. And the initial velocities of the objects, so I have velocity A and velocity B before the collision. Right? What is the final velocity of the two objects stuck together? All right, do you guys think you can solve that? So I'll solve it up here. You guys solve it? I'm going to solve off this paper. Okay. If you're lucky, maybe you have the same numbers I do, but probably not. Okay. But we all have the same framework. So this is number 5. Here's my framework right here. Sum of momentum initial equals sum of momentum final. Okay. I start off with 2 individual objects. Mass A, velocity A initial, plus mass B, velocity B initial. Okay. So there's momentum from this one, momentum from this one. And then because it's inelastic, I'll write down that word, inelastic. Okay. Because it's inelastic, I know that they're going to stick together, make one giant MA plus MB, one giant mass. Move together at some common final velocity. That's what I'm solving for. All right. You guys get that? Okay. So let's see, I got some values right here. Let's start plugging these in. Yeah, 1 kilogram versus 4.5 kilograms. Let's try it. So we got 1 kg here, and your numbers are probably different than mine. 5 kg here. I just made up some random numbers. Okay. Okay, and then on this side, I got, of course, the same masses, but now they're stuck together. All right there. Right. Velocities. Okay, I have to know how fast and what directions. So 7.5 versus -1 meter per second. This is 7.5 meters per second. This is -1 meters per second. Okay. It's important you get the signs also. Okay. Because here, if you forgot to put the negative or something like that, then it'd be the difference between like a fast car running into a slow car, fender bender, versus if they're like coming opposite directions. Okay. You get different results. It's vector quantities. Okay. And so final velocity right here, that's what I'm solving for. All right, there's the setup. You probably have the same setup, just different numbers on your paper. You guys got that? All right, now what? Well, maybe I'll throw in a middle step. I wonder how much momentum is ever in the system. So it's that. Okay, I'm looking at, okay, I have this many kilogram meter per second of momentum on within my system. Right? Oh, by the way, there's no name that I'm aware of for a unit of momentum. So I'll just call it kilogram meter per second or just unit of momentum. I don't think it has a name. I don't know. Okay. And that's going to result in, okay, this now giant mass, which is now this many kilograms, moving at how fast is the question. All right. You guys got all that? Right. The kilograms goes away. So the unit I'm left with is meters per second, which is really nice because that would definitely describe a velocity. So just divide down this number, divide down the kilogram. So whatever 3 divided by 5.5 is 3 divided by 5. Okay. So look at final velocity is equal to, I'm getting this many meters per second. Okay. Let me just make sure that's an answer choice on the paper. Ding. Right there. Oh yeah, I'm good to go. Okay. Is that also working out for you guys? You guys getting an answer choice on your paper? Okay. So while you guys are finished with that, checking your answer, go recap this again. So it's a collision. I know the property is going to be momentum is conserved. So that's my first setup here. Sum of momentum before equals sum of momentum after. Okay. Then I can add all the momentum bits before. I get like this. Okay. And I say, well, after it must be the same. So I can say equals. Okay. Now, since they stuck together, that's inelastic. They made one giant mass. And I could just do a little algebra and solve for that final velocity. Okay. All right. Also, while you guys are finished with that one, here, I'll throw another idea that's going to connect to some ideas later today, which is I wonder what happened to energy or kinetic energy during this process. Right? There's a reason that we're not using energy as a method to solve collisions, and you guys will see why. Okay, so let me kind of take a step back and let's go to that real basic example of two objects, same mass, same speed, opposite direction, collide and stick together. Okay? So maybe they got like 1 kilogram at 10 meters per second and 1 kilogram at -10 meters per second. And they collide and stick and go to 0. Okay. Well, guys, when they were in motion, did they each have a bunch of kinetic energy? 1/2 mv squared, 1/2 mv squared. That's like 100 joules, 100 joules. Isn't that like 200 joules of kinetic energy? Right? It's a scalar, so it would add up. So it's great. We've got like 200 joules of kinetic energy. But when they collide and stop, suppose they're asteroids in deep space, and now they're just not even moving at all. How much kinetic energy is that? 0. If you run 1/2 mv squared, that's what kinetic energy is. 1/2 mv squared, you're 0. Hold on a minute. We just started off with a bunch of energy. Now we went to 0. I thought I taught you guys like 2 weeks ago that energy was conserved also. Where'd all the energy go? Huh. Do you think maybe if these asteroids smash together, there might possibly be some permanent deformation? Ooh, I bet there's some force times distance that goes into smashing these things. How about if you put a thermometer on this? Like, ooh, do you think the temperature goes up a little bit if I'm smashing them together? How about, ooh, hey, do you guys hear that? Is that sound vibrations? Do you think some of that energy is leaving as sound vibrations? Okay, so that's all different places the energy goes, right? There was a bunch of energy before, not so much after, right? So the kinetic energy score actually does change, and you can't really use that very effectively to solve for collisions, right? But momentum solves collisions really nicely. Okay? But I don't know if this is a little bit overkill, but I'm gonna numerically solve that. So I know kinetic energy is 1/2 mv squared. Let me do some pink ink, this little thought bubble over here. So what's kinetic energy initial versus kinetic energy final, pre and post collision? So I'll do 1/2 times this m times this v squared plus 1/2 times this m times this v squared. I could drop the negative even because it's squared, doesn't matter, it's a scalar. Okay, I'm getting about 30 joules, 30 and change, so I'll just call it 30 joules before the collision. How about after the collision? 1/2 times this combined mass times the v squared is, like 0.8 joules. You guys see it went from 30 joules to less than 1 joule? And sometimes it's not that extreme even, but it definitely decreased. Is that okay? Do you think you can have a collision where the kinetic energy ever increases? No, that'll never happen. Okay. At best, the kinetic energy could stay the same. We'll talk about that later. But usually it goes down. In fact, for perfectly inelastic, it has to go down. Okay. I could make it any crazy set of numbers. In fact, you guys all have different numbers on your papers. I bet for every single one of you, if you check kinetic energy, I bet it goes down. Okay. Is it? Right, guys, good? All right. And again, perfectly inelastic, that was the lab that you guys did before the break. Right, so you guys go with perfectly inelastic? Okay. All right, next one. Let's look at a whole spectrum of types of collisions, because here's kind of where we're starting, but I want you guys to see the full forest for the trees roadmap before we embark on this adventure here. We just did this one where they stuck together. Right? Now, what's going on with momentum? What's going on with kinetic energy? And we just talked about that, right? So, by the way, here, just point this out. No matter what type of collision, momentum is always conserved. So this box is just copy pasted. Momentum is always conserved. We're using that as a framework to solve these, right? The kinetic energy, and I just showed this to you. Kinetic energy actually decreased for that collision. You guys saw that too, right? All right, so what other type of collisions could we have? Well, perfectly inelastic because they collide and stick, right? Now, later this week, I'm going to pull out a bag of balls and have you guys bounce these balls, and you're going to do some measurements related to these. That'll be a different lab, right? But for today, here's one of your collisions. That ball didn't bounce at all. Does that look like perfectly inelastic? I bet this like this right here, right? What about what about this nice bouncy ball here? Boing, 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 boing. Look how bouncy that is. Woohoo, I love to bounce. Boing, boing, boing. That's going to be this one right here called perfectly elastic. That's complete other end of the spectrum. Actually, I have a better version of that. That's actually this right here. You guys see Newton's cradle, right? Newton's cradle. Okay. This is one we're about to be talking about. Is hey, look at that. Look how bouncy that is. That's probably as close to perfectly elastic as I can get. And I'll talk more about this one later. But boing, boing, boing. You guys see that? How bouncy that is? Right. So I got really bouncy. I got not so bouncy. And then do you guys see this one in the middle? It says general conservation momentum, right? So that could be somewhere in the middle. So here's your spectrum from perfectly sticky to perfectly bouncy. You guys see that? Right. So got some more about later, right? And we'll talk about the explosion near the end of class today. Okay. Right. Guess that. So there's your full forest for the trees, different types of collisions get out, right? All right, let's just do a general one. So we're going from this perfectly inelastic where they stick together. We're just going to do a general case. You guys ready to do a general case? All right. So actually, most years I usually start with this one. So do this one here, right? So I got two objects. Maybe different masses, maybe different velocities. They're going to collide, and then what? Maybe they stick, maybe they bounce. Maybe, hey, do you think if I had two half-deflated tennis balls, they bounce off each other, but not very well? Yeah, those are bouncing, but not that great. You guys see that? Okay. But regardless of which type of collision that is, this conservation momentum always applies. That's what I showed you here. Yeah, different type of collisions, but you guys notice momentum is always conserved for all these, right? So we're just doing a general case here. So I can say, if I add up all the mass times velocity bits before the collision, and I add up all the mass velocity bits after the collision, regardless of it's bouncy or not so bouncy or anything in between, it always, always, always is conserved. Okay? Is it? Right. Let's do number 3. You guys ready to do number 3 on the page? Number 3. So this is just a general collision. Two objects. Okay, I gave you these measured masses. They collide head on. Yep, so we're just staying on the x-axis, one dimension. Right? Result in these given measurements. So here's the pre-collision velocities here, right? And then I gave you one post-collision velocity, and I'm asking for what's the other post-collision velocity, right? So what yeah, what is that? Try to figure out. So this is number 3 right here. So here's your framework. Sum of momentum before the collision equals sum of momentum after the collision. I like that. Okay. Now before, all I'm doing is just following this. In fact, this is one of your thumbnail notes if you have your blue banners out, or you guys see these posters hanging in front of me right here. So if I cover this up and you need to reference it, it's just a poster hanging in front of me right now anyway. Okay. So what do we got? Got if I do mass times velocity for object A before the collision, plus mass times velocity for object B before the collision, that's some amount of momentum in the system. Then after the collision, do MAVA final plus MBVB final. It has to equate. Therefore, I can solve for the unknown value. All right, let's plug some numbers in here. Something times something plus something times something plus something something plus something something. And I'll have some kilograms here. I'll have some meters per second here. It's mass and velocity. Well, okay, I'm solving for a VB final, so solve for that guy. Right, but I have numbers for all these other ones. Okay. So let's go number shopping here. I'm just gonna pull off this page. I've got 4 versus 3 kilograms. So 4 kilograms versus 3 kilograms. And what's it got? Okay, my object A was going 7 meters per second. So put that right there. My object B was definitely headed the opposite direction because it's negative. Right? Well, yours may or may not. I don't know. But mine is having head-on collision opposite ways. Right? Then post-collision. Right? See, like here, if I stop right there, if that's all I gave you, if I gave you the masses and the pre-collision velocities, you would not be able to solve this yet. Because you don't even know, right? Is it a bouncy collision, a sticky collision, a half-deflated tennis balls collision? There would not be enough information with that right there. You cannot solve that unless I tell you one more piece of information. I could say inelastic, that could do it. Right? Or I could give you a number. And it looks like here I gave you post-collision velocity of object A. And for me, I have this many meters per second. Okay? And since it's negative, I have to definitely put the negative in there. Right? That means it rebounded maybe the opposite way. So it bounced off. So it's like the boing, maybe something like that. I can solve for what happened to object B. Right? You guys get that principle? Okay, so you guys are solving yours. I'm solving mine. Let's see how much momentum is in my system. Got 4 times 7 is 28. So it's 27. I think that's positive 1. The kilogram meter per second right there. Okay. This is 16 kilogram meter per second there. Got 3 kg BBF. Okay. You guys good? Okay. All you need to do is add this over, divide by this coefficient mass. So this many kilogram meter per second divided by this many kilograms equals BBF. Right. The fact that it's positive means I know it's going to be headed back towards the opposite way, right? Which I think makes sense too, because this is kind of what just happened. Boing, if something like that. Boing. The kilogram unit cancels, whatever that is. 3. Okay. I'm looking at velocity of object B final. So post collision is, my calculator says this many, and that would be meters per second, which describes the velocity. Yep. All good. All right. Just make sure it's a answer choice on my paper. Do I have? Yeah, I got it right there. Yep, it's an answer choice, so we're all good. All right, so you guys are getting that on your paper too? Yeah. So there's just a general collision. All right. All right. So while you guys are finished with that, give you guys a quick recap. Is remind you guys back to your lab before the break. That was perfectly inelastic, and then we solved that one. That was number 5. Right? We said, hey, well, what about just a general collision where they sort of bounce off each other, regardless of how they bounce off? So we just did a general setup, general conservation momentum. Okay? And a lot of times in the past, I usually start with that question. Okay? All right. All right, guys, good? And I think the next best place to go is the other end of the spectrum, which is perfectly elastic. Right, you guys ready to talk about perfectly elastic? Okay? Perfectly elastic is perfectly bouncy. All right, so perfectly elastic. Let me find my poster for. Right, so I got my general case there. All right, here we go. Here's perfectly elastic collision. And what makes something perfectly elastic? Like I've been saying, perfectly bouncy. Give you guys a physical example first. So like this bouncy ball is probably a pretty good example. It's just so bouncy. Look how crazy bouncy that is. Okay? Or it's Newton's cradle, right? So probably this right here. This is actually showing both conservation of momentum, but also well, here, also this conservation of kinetic energy. That's what makes this perfectly elastic, right? Not only is momentum conserved, which is true for all collisions, so that's not super special, right? But this property right here, if kinetic energy before is equal to kinetic energy after, that is the physical marker for perfectly elastic, like perfectly bouncy, right? Now, this isn't perfectly bouncy, but it's probably close as I can get, right? If you set this up and you set this in motion, it's going like bounce, 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 right? And you like lock this away in King Tut's tomb for 10,000 years and come back and dig him out of these going bounce, bounce, bounce 10,000 years later. Like that would be perfectly elastic. Right? And this is probably pretty close. Right? Let this go. It's slow down there. Right? All right. So what's going on with this map? This is a system of equations. So yes, momentum is conserved. All the mass velocity bits add up before and after the collision. Right? Kinetic energy is also conserved. Again, this is particular to this collision. Like only this collision is that true. If you solve the system of equations, this is the answer. This is the solution. The system of equations. This is always this gold box here. This says the post-collision velocity of object A is, and it's this giant fraction. We're going to solve that, right? But tell you guys some things about this. Is first of all, I'm not going to have you guys. I wouldn't expect you to solve this from scratch in class or memorize this for that matter. Like if I wanted you to apply this, then I would give this expression to you. If you solve this in college, then if you take physics in college, at least when I was taking this class, they did expect you to solve this from scratch. But it takes a lot of paper and it takes a lot of time. And also, this gold box formula right here is not in a lot of physics textbooks. And it's also really hard to find on the internet. So hold on to this page from high school when you go to college, if you take physics, and it might save you a lot of paper and a lot of time. Okay, you see that? All right. What else to say about this? All right. I'm gonna make a note for my AP classes. So I'm making this video for all my classes. Here's for my AP students. AP usually asks a couple of questions about elastic, but they don't expect you to solve this from scratch either. What they usually do is, if it's a multiple choice question, what I tell my AP students is take advantage of the multiple choice. So if they say like, which could be an elastic collision, and they'll give you options A, B, C, or D, and I'll give you like a table of masses and velocities. And what you should really do is go through the answer choices, start at option A, right? And test, especially this kinetic energy expression. See if kinetic energy is conserved, right? And if it is, that's usually the answer. And if both of these are conserved, that's definitely the answer, right? And if it's not conserved, then that's not elastic, right? And the other question that AP likes to ask, and I've seen them ask this a few times before, is they'll have some setup where it's a very basic elastic collision. And I'll show you to you right now what the collision is going to be. So it might be a free response question, and this might be one step in a multi-step question. So I'll have two masses that are the same mass. Hey, look, that's this right here. This mass and this mass, they're the same mass. And they'll have one starting from rest, and another collides into it. And guys, if it's elastic, what's going to happen every time? Boing, you just saw it. You guys see that the one that was moving came to a dead stop, transferred all its momentum into the other one? Boing, you just saw it again, right? So boing, that motion right there. Boing, AP loves to build into free response questions. So it's like one part of a bigger question, okay? Right, so without necessarily digging into all this crazy looking math. Right, okay, so you guys get the principle of elastic collisions? Let's solve one of these. You guys ready to solve one of these? All right. So the question on this half page is number 7. You see number 7? Two objects given masses collide head-on perfectly elastically. Hey, that's this right here. What therefore is the final velocity of object A? So I gave you the two masses. I gave you the pre-collision velocities. And it looks like mine are sort of headed towards each other because it's got positive and negative. Right. Now, again, if that's all I gave you, you wouldn't be able to solve this. But the fact that I threw in one more piece of information, I said it's perfectly elastic. That means now this is solvable. What is VA final? It's set up right here. So this could have been the hardest question, definitely. But now it's sort of the easiest question because the answer is right here. There's no algebra even. It's all arithmetic at this point. All you have to do is plug it in. So you guys go ahead and plug yours in. I'm going to plug mine in. All right, so this is number 7. All right, I'm going to cut straight to the answer. Velocity A post collision is it's a giant fraction. It's velocity A initial. It's a vector times the difference of the masses, MA minus MB, plus 2 times mass B times VB initial. Get that here. All divided by sum of the masses. Mass A plus mass B. Something like that. All right. So all that in parentheses. Okay. So I just copy that straight from, that's always the answer to this question, to this system of equations. I need some numbers. So what are my numbers? So my masses are like 2 and 2.3 kilograms. So I'll go ahead and plug that in. I got 2 kg right there. 2.3 kg right there. Also shows up right here. Also shows up down here. kg, kg. Okay, I got my masses plugged in. Okay, now I need some velocities. So VA naught, I got right here. This many meters per second. Okay. Okay. Oh, don't forget this factor 2 right here. And then V naught, I got bam right there. It's like negative per second. Okay. If it's negative, don't forget the negative because these are vector values, so that's gonna matter. Yeah, like a head-on collision. All right. So as long as I plug this in correctly, I should get the correct answer. Let's see if I do. So I got whoops. Just got minus right here. 2 minus 2 to 3 plus 2 by 2 by negative 3. And then 2 plus 2, 3. All right, I think I did that right. Let's see. My calculator's, let me double check, make sure that's an answer choice. Yeah. Okay, I showed up. Yeah, that's one of the answer choices on my paper. So I am good to go. There you go. Yeah. All right, is that working out for you guys too? All right, so while you guys are wrapping up that one, I'll throw some other questions at you guys. Okay. Suppose I did see if you guys are following. Suppose I did a kinetic energy check. I said, well, before the collision, I had a bunch of 1/2 mv squared, and I could add all that up and get some number of joules. After the collision, I could also add up all the 1/2 mv squared bits and get some number of joules. Guys, what would happen to kinetic energy in this type of collision, which is elastic? Is there more kinetic, does kinetic energy increase, decrease, or stay the same? Stays the same. That's right. You guys did remember that. Okay, because we're talking about this special kind of collision right here. Okay. Oh, and by the way, that was also one of the expressions that goes into the system of equations to begin with. Kinetic energy is conserved. That's what leads to this gold box. Okay, so you could run this check, kinetic energy check, and it'll always stay the same. Kinetic energy before the collision equals kinetic energy after the collision. That's part of it. How about this? This right here is the answer for the post-collision velocity of object A. What if you want to know what happened to object B? Who can think of a way that you could solve for? Here's VA final. Who can think of a way to solve for VB final? How could you do that? Yeah, you figured out the tricky way first. Yeah. All right, yeah. Which is, you can just change the definition of what's A and what's B. Can I call this B? And then B, A, B, A. I can just swap what's the definition of A and B. I can do that, right? Another way you can do it too is once you know velocity A final, could you just take that, plug it into either one of these equations up here and solve for either, or actually, sorry, you plug in here, and you can solve for this or this. You did that with T, right? So there. So there's different ways to do it. This, okay, that's it. All right. Where are we here? All right, so let me find that roadmap. So what have we done so far? Right, so we start with perfectly inelastic. That was your lab that you did back on Friday. Then we solved a general case that was number 3. So here's number 5, here's number 3. We just did number 7. Okay, we did all that. Okay. What have I got next? Here. Okay, this will look a little bit off the beaten path, but it's gonna wrap around and connect to the next thing that we're doing. This poster and the next 2 posters are new. You don't have these as thumbnails, but if you download that book that I posted this morning, then you get all these new posters. These are all new right here. So 2 asteroids collide. So we're out in deep space. There's no frictional losses, definitely nothing like that. Okay. Now here's an interesting tidbit that's going to connect back, is that if you just focused on the center of mass of the 2 asteroid system, you would never actually know when that collision happened, right? So notice I'm not focusing on either individual asteroid. I'm just focused on the center mass of the 2 asteroid system. Okay? That center mass is unaffected by the collision itself. So if it's in motion, it just keeps moving, same velocity as it was before. Okay? That's true regardless of the type of collision. If it's elastic or inelastic or anything in the middle, that's always true. That's true in 1 dimension. But if you pull this out to 2 dimensions or 3 dimensions, that's still true. So if the center mass is at rest or if it's on the move, you would never know when that collision happened. Okay, so hold on to that fact. So that's fun. By the way, for my AP students, AP loves asking this particular question. So look for that on the AP exam. We'll see that question. Okay, but there's some variations on that question. So actually, these are all sort of related to each other. Right? There's a hey. You guys remember that Magic School Bus clip before the break? Remember Magic School Bus? Here's Magic School Bus. This was inspired by that. Okay, so. Here, I have throwing a snowball on an icy surface, but you guys saw the version where she was throwing a baseball on a frictionless baseball surface. It's the same story, isn't it? Same story? Okay. Now, guys, if you're standing on the mound with the baseball at rest, how much momentum is in the system at rest? Zero. Zero momentum, right? Now, momentum is conserved. Okay. This is sort of like a collision. I've been saying we're going to use this for collisions, but this is sort of a collision just in reverse. Okay. So if you throw the baseball heads off one way with a bunch of momentum, say towards the left. The pitcher's going to end up with some momentum back towards the right, but it still has to zero out. There's still zero momentum in the system. I think we did actually solve this. If you look back in your notes from, it's either Thursday or Friday back in the day, I think we solved this. If I gave you the mass of the pitcher, the mass of the baseball, and the velocity of the baseball headed towards the plate. 1, 2, 3. 3 of those 4 bits. You can solve for the velocity of the pitcher headed back towards second base. And I think that should be in your notes. You guys got that? I think back on Thursday is what it was. Right? And we solved that. Right. So now here's another tidbit that goes hand in hand with that. If you look at the center of mass of the 2 object system, the ball and the pitcher, does it ever move? No. Because it was never in motion to begin with, and there's no external force. I mean, there's an internal force throwing the ball, but no external. So the center of mass actually never moves. It just stays over the mound the entire time. Okay. All right. There's also a variation on this one, which is the grenade question. We're going to do a grenade question today. Okay. So suppose you launch a grenade, and what if it never explodes? What if it's a dud? If it's a dud, is it going to follow a nice parabola path and land probably right about there? Do you guys think? Yeah, it'd probably do that. Right. What if it does explode, maybe in midair, and it could explode anywhere? This would still be true. Doesn't have to explode at the top, but maybe it explodes into 2 parts or 3 parts or 1,000 parts. Maybe it turns into fireworks, something like that. If you followed not any individual piece, but if you followed the center of mass of all those bits, guess where the center of mass lands? Exactly where the dud landed if it never exploded at all. Same place. The center of mass never actually changes due to the explosion. The center of mass is unaffected by the explosion. Can I say that too? All right. We're going to take advantage of that to solve one more of these. All right. And by the way, what I've just been showing you, those last 3 posters, is all those last 2 actually, some version of this one right here. You guys see explosion, right? So when you see an explosion in physics, think perfectly inelastic collision, just in reverse. So if you throw a baseball on a frictionless baseball field, throw a snowball on an icy surface, a grenade explodes. Right? If you ran that film in reverse, it would look just like a perfectly inelastic collision, wouldn't it? Right? Yeah. So momentum is still conserved. Right? But the kinetic energy, guess what happens to kinetic energy during an explosion? Does it increase, decrease, or stay the same? It's going to increase. Right? Now that energy comes from somewhere. A grenade, it's easy. It's just a chemical reaction. Pow. Right? Throwing a baseball. Does the energy probably come from the pitcher's muscles, you guys think? That's where the energy came from. Turned to this mechanical energy called kinetic. Okay, you guys see that too? All right, let's solve one of these. So it's going to be number 6. on your paper. You guys see number 6 here. It's a grenade flying through the air at some given velocity, explodes into 2 parts, which travel along the same direction the grenade was originally traveling. At what velocity is piece B of the grenade traveling? Can't apply perfectly inelastic, just in reverse. So I gave you the mass of each grenade part post-explosion. I told you how fast the grenade itself was originally thrown, which is the number at the end. I told you the post-explosion velocity of one of the pieces. Right? So maybe we're like hunting around on the ground. Where's the other piece or something like that, right? Well, here we're trying to solve for how fast, right? And what direction, like a velocity. Fine. That's pretty close to this poster right here, actually. Not exactly. Or maybe I'll just get my grenade poster. It's a little bit closer, like this. All right. Anyway, whichever one you want to play off. Let's get some numbers on the board here. So this is number 6. So here's my framework. Sum of momentum before the explosion equals sum of momentum after the explosion. Right? Is that? Okay. Now for the grenade explosion, I'll call this explosion. More obvious what we're looking at. Right. So we're looking at an explosion situation. The grenade used to be all one giant mass. So I'll put that over here. Mass A plus mass B was all moved together at some common final, or some common initial velocity. Maybe I threw it. Okay. Okay. Then post-explosion, I got mass A moving at its own velocity A. I got mass B moving at its own velocity B. That can make sense, right? Yeah, that does look like inelastic collision, but in reverse. Because if I just reverse the left and the right, that would look like inelastic collision. Okay, so let's try here. Okay, so I just need some numbers. Here, I got some numbers here, I guess. We got here. So this paper, I've got 0.4 and 0.6 kilograms. So this is 0.4 kg, 0.6 kg. So it looks like I had a 1 kilogram grenade to start with. It was all just one giant kilogram. That could be this right here. And looks like I threw it this fast on this paper. So this many meters per second. Right there. And then post-explosion, I got piece A. So back to this many kilograms. Moving VA final, this many meters per second. The fact that it's positive, I know it's going to head in the positive direction. Okay. Now piece B, I got is, I know how many kilograms. So already. I just got to find how fast is piece B moving post-explosion. Right. Oh, yeah, I can definitely solve that because that could be an algebra equation, one unknown value. Yeah, I can solve that. Okay. So throw in a middle step here. Looks like I had this many kilogram meter per second of momentum in the system. What's this? Wait, is this? I know what this is. It's like this many. Oh, hey, I've got really nice numbers on this one. That's lucky. Yeah. Yeah, like that. Like that. Okay. See, subtract that over to be this many kilogram meter per second. And then the next algebra step is to divide by this mass right here. That give me VBF. The kilograms goes away. And then velocity B final, so post-explosion is, I'm looking at this many meters per second. Okay. And is that number on this paper? Aha, right there. So I am good to go. That'll be it. All right, so you guys good? Good. All right. Since we got a couple of minutes, all my other classes, that's been the point of it wrapping up, and then the bell's been ringing. Right. For you guys, since we got a couple minutes, real fast, let's look at these other questions. So we've done 1, 2, 3, and 5. We're going to come back to number 4 later. Number 4 is also a general collision. We're just finding pre-collision information on that one. Right. We did 6 and 7, and then all those other ones. Okay. So number 8, number 9 are trying to address the question, how bouncy is a collision? There's a physics term for that. It's called coefficient of restitution. It's what distinguishes this from this. I love bounce. That's two different collisions there. Reverse this one. I kind of like to bounce, but not as much as the bouncy ball. Okay. So how can you find the coefficient of restitution? So we'll talk about that 8, 9. And then 10 and 11 is getting at an idea called impulse. It's if you transfer momentum to something by applying a force for some time interval. So I know I got a poster for that for sure. Whereas, here we go, right? This is going to be an important poster that my other classes hadn't quite got to today, but in the near future, we'll do that one. All right, so that is otherwise a wrap on today. Guys, remember to check those files I posted to Google Classroom this morning. So there's a new book of posters, an updated book you guys can get. And if you're in 10th grade or have a 10th grade friend, you have an Excel file for testing tomorrow.